then I'm going to go ahead and share my slides and just check in that folks can see those.
Looks good.
Okay. All right. Well, yes, thank you very much, Tony, and thank you all for attending today. I really appreciate the opportunity to give a talk on maybe to persuade a few more folks to be interested in brown dwarfs on a galactic perspective. I think back then we were primarily interested in just discovering and characterizing brown dwarfs, and that field has really moved on to start to use these objects as a tool for other science. Both in the exoplanetary regime, in the regular stellar regime, and hopefully I can convince you that increasingly these will be important tools for understanding our Milky Way galaxy at large. So before I go on, I do want to make a pitch because it is my opportunity to do so. We have a new graduate program at UCSD, a new astronomy PhD program that we just started this year. We are accepting applications for this coming cycle. The applications are due on January 12th. And so if you are a graduate student, or sorry, if you're an undergraduate student, or an undergraduate student who is looking to go to grad school in astronomy, please take a look at our program. We're brand new, and we're really excited to bring in some folks to use some pretty amazing tools that we have here in the UC system to study the universe. Okay, so I want to start with our recent news of the Decadal Survey. I was privileged to be able to serve as part of the survey on the panel for stars, the sun, and stellar populations. Of course, like everyone else, I was waiting for a long time to figure out exactly how that work was going to be processed along with everything else. I perhaps was disappointed that brown dwarfs didn't turn out to be the most important science objective for the next 10 years. I guess I'll just have to live with that. That's okay. But I think one of the things that came across is I was sort of reviewing some of the key scientific priorities for the next 10 years that were kind of merged in the survey. And you can see them listed here: worlds and suns in context. This is largely about studying exoplanets, particularly habitable exoplanets, and their relations with the stars that they orbit, or how they form, et cetera. The new messenger and new physics category, which I think in some degree focuses on sort of compact and extreme objects and the sort of new tracers we can use to study those, including neutrinos and gravitational waves. And then, of course, sort of the much greater topic of galaxy formation and evolution, and particularly how galaxies grow in mass over time. These all seem very, wide, dispersive topics, but I also see a sort of underlying connection between all three of these things, that they all involve the Milky Way in some way, because, of course, there's this adage that, know thy planet, know thy star, and I would argue, know thy galaxy, know thy stars, right? You don't really know anything about the stars or the exoplanet hosts unless you actually understand the more wider galactic population, things like the star formation history, the Metalyses distribution, et cetera. And so understanding our population of planets is also going to be important for understanding our population of stars to see how those various formation mechanisms propagate through. When we talk about new messenger physics, a lot of the work is, of course, on looking at extreme events, gamma ray bursts, fast radio transient, things that are kind of the edge of the universe. But I would argue that, first of all, most of our new messenger physics, at least when it comes to neutrinos, is a local study, right? We think about the sun, we think about supernova 1987A. Certainly with the upgrades that will be coming with IceCube, we'll be starting to detect the supernova background and potentially the cosmic microwave background in neutrinos in the distant future. But for the near term, a lot of our neutrino physics is going to be coming from Milky Way supernova and events that happen in the at least extended Milky Way environment. And of course, I would argue also some of our best compact objects are close to home, including Sagittarius A star. And so if we really want to understand how black hole mergers, neutron star mergers happen in the distant universe, it's unlikely we will see one in the Milky Way, but at least we can study their progenitors here in the Milky Way much more easily. And then, of course, galaxy evolution is a much broader topic, a wide range of different galaxy populations, different morphologies. But again, we have this system very close to home in which we can anchor those studies, at least from the perspective of spiral galaxies. And of course, those studies also inform our own understanding of how the Milky Way assembled and formed over time. Being able to see the satellites of our neighboring galaxies in much greater detail, for example, allows us to understand the satellites that are harder to study from our particular perspective in the Milky Way. So all of these, I think, are tied to some degree about the Milky Way. And so, I would argue that a lot of our key scientific challenges that have been identified in the Decadal Survey do require really focusing also on the Milky Way and improving understanding of its, not just its current environment, so its current structure and its current satellite systems, but also how those evolved over space and time. And so throughout this talk, I'm going to refer to this topic of galactic archaeology, and I would strongly recommend folks who, I think a lot of you are actually quite masters of this topic. Those who want to learn more, I would push you to the recent survey by the recent review by Helmy, where she actually has a nice description of how this term galactic archaeology came into existence and how it's, there may be actually agreement on what this actually means. So I wanted to define at the start that I'm really talking about how we understand the whole history of the Milky Way over space and time, particularly through the tracer populations that we use, and those are the stars within the galaxy. So the breakdown of my talk today, I'm going to be focusing on kind of doing a quick review of some of the recent advancements in galactic archaeology. But the main point here is I want to sort of turn this into how do we take what we've learned today and perhaps learn something new or learn it in a different way by using a different stellar population that's been traditionally used for this work. And that's going to be the ultracool dwarfs. So I'm going to take some time to explain what the properties of these objects are and really go into detail about why, why I think and why scientifically there seem to be reasons where ultracool dwarfs may actually be a particularly ideal population for studies of galactic archaeology, at least in the future, where we're going to have large samples of those. And then I'm going to introduce a couple of studies that my grad students have been doing over the last few years to kind of do Pathfinder experiments on this, this topic. And they are Pathfinder because, as I'll mention, ultracool dwarfs are really found local to the solar neighborhood because of our sensitivity limits. But the things that we're learning from those studies will be generally applicable in the next 10 years as larger scale surveys come online. And then I'll focus then on some of the expectations that we have for these future surveys, including ones done by James Webb, hopefully very soon, and some of the other surveys in the near future as well. Let me start with some context on galactic archaeology. And of course, this is going to mostly talk about Gaia because a lot of what we've sort of evolved to know about the galaxy has really kind of exploded in the last few years because of the data, the exquisite data that's come from the Gaia satellite. It's good to kind of keep this in context that often when we introduce galactic archaeology in our classrooms, graduate classes or undergraduate classes, we usually show a picture like this. It's largely focused on kind of the structural elements of the galaxy, right? The spiral arms, the bar and the bulge, the halo and the disks, various globular clusters. But I think it's important that galactic archaeology doesn't just talk about today's current, picture of what our galaxy looks like, at least at this core scale, but also how it's evolved to this point over time. And so some of the tools that are really important for this work are, of course, the stellar populations that provide not only the dynamic and structural traces, right? They are actually illuminating the sort of, where the mass is, at least the baryonic mass is in the galaxy. But they also span cosmic time. And so in particular, if you have stellar populations that are long-lived, you can take these as not only sort of time capsules of the conditions of the galaxy when that star formed, but of course, they also become dynamic objects that get perturbed over time. And so they'll trace the evolution of these various events that built up our own galaxy. For that, we really need very precise spatial and kinematic measurements of the stars. Of course, Gaia has been extremely important for that. But also we also need precise physical properties of these stars. So these include masses, ages, and abundances at the first level. But there's also detailed abundances, right? Not just metallicity Fe over H, but also what is the alpha enhancement? What are individual elements that may be of interest in tracing various nucleosynthetic stages of chemical enrichment in the history of the galaxy, and other events like that. And then we also need the right models, right? So in order to actually piece out these physical parameters, we need to take our observational data and map them onto true physical parameters. And so as I'll talk about, at least when we get to the ultracool dwarf regime, we actually need to keep working on that part of it because there are many cases where we don't have accurate models to actually infer those physical properties. And then most importantly, we need to have a really large sample, right? We can't do this with a population of 20 stars. We need to be getting into the scale that we have with Gaia now, kind of in the billions of stars, where we can see not only the sort of bulk average properties of our galaxy, but perturbations to those that trace important events in the galaxy's history. Now, again, any talk about this is going to have to start with Gaia, so I'll get through it as best as I can. But it has really been a revolution in sort of our understanding of galactic archaeology because of the precision kinematics and the precision positions and the just sheer large sample of stars that have been observed with this study. I think some of you have seen this image before. This is the Gaia EBR3 star count map. So this is not a traditional image of the galaxy. This is really just a map building up the density of stellar sources across the sky. And I think this is actually a really interesting view because not only do you see the traditional structures that you expect from the Milky Way, the disk, the sort of extended halo, but you also see some structures that point out primarily because they are, stellar density measurements as opposed to stellar brightness. So one of my favorite from this part is the fact that you can see part of the Sagittarius dwarf spheroidal here poking out below the galactic bulge. Of course, it's in that direction because that's Sagittarius. But the fact that you can actually see this visibly in this kind of map, a structure that was, really discovered only in the last couple of decades, is a real testament to how far we've gone in terms of our ability to measure the stellar population around Milky Way. And of course, you also see the Magellanic satellites, which you can see with our naked eyes, but also globular clusters. Even Andromeda shows up in the Gaia star counts. But I think, one of the things that we are most, at least from stellar astronomy perspective, most enthralled with in terms of the Gaia data is the absolutely exquisite color magnitude diagrams that come out of this. I think everyone that's been teaching stellar astrophysics in the last 2 years has shown this plot at some point in their class. It's a really amazingly beautiful main sequence that shows not only the sort of key properties that we describe in our undergraduate courses, the main sequence and the giant turnoffs, but also details within those structures. So, you have all the sort of overdensities in different parts of the giant population space that track, different stages of evolution. We have the splitting of the white dwarf track that came from Gaia data that really shows you the splits between the different compositions of hydrogen, helium, white dwarfs. And lots of other things that pop up in these kind of diagrams when you get the kind of sheer scale and precision of a data set like Gaia. But of course, Gaia also provides a lot of detail in the kinematic space as well. And I think that's where a lot of kind of the interesting dynamical and historical studies of the galaxy have kind of taken off. This is a plot from Hunt et al. 2019. I think this is based on either DR1 or DR2 data, showing just locally in the solar neighborhood some of the structures that appear in kinematic space. And these structures, to some degree, have been known in the past. We can measure these things like the Hyades and the Pleiades structures, the moving groups in those. Some of these are moving groups. Some of these are resonances with structures in our galaxy, but they show up in kinematic space very clearly, particularly when you have the precision of Gaia to sort of sharpen up those features. And we also have beautiful maps now of the outer parts of our galaxy. So these include all the various streams and overdensities that trace the tidal disruption and sort of infall of stars from the satellite galaxies over time. So again, some of these structures are named here. You cannot possibly read this, so I encourage you to take a look at the Helmy review to kind of see what the state is for those streams. But many, many dozens of streams have now been identified, in large part because of the extremely exquisite astrometry that's been provided by Gaia. Now, again, when you start to get these large samples with precision measurements, you can start to see perturbations to the sort of standard distributions. So this is, I think, it's a very famous result showing these vertical wave oscillations in the galactic disk. So this is showing just sort of number density as a function of the sort of scale height away from, or the distance, vertical distance away from the galactic plane. There's sort of a sort of standard kind of secant squared or hyperbolic secant squared sort of distribution here. And then there's perturbations off that show these sort of oscillations of vertical waves. And those are believed to be caused by perturbations, and particularly from the satellite galaxies like the Sagittarius dwarf spheroidal. And similar kind of perturbations are seen also in phase space. So this is a look at the vertical velocity versus position and color-coded by the velocity going around the galaxy. And you can see this kind of beautiful snail spiral structure here. Again, a perturbation effect, kind of a ringing of the galaxy as traced by the stars that are perturbed by these dynamical events. Now, the important thing is that Gaia is not the only thing that's been important for this work. We have to keep in mind that a lot of the measurements really come from adding on to the astrometry and photometry that comes from Gaia. And so Gaia provides kind of the first 5D of these measurements, but there's many other Ds to add on here. In particular, if we want a full 3D kinematic picture, we need to add the radial velocities. And that's largely been coming from high resolution spectroscopic studies like Apogee, Gaia, and others like that. But then also, as I mentioned, stellar properties are critical to this. So you need to know things like the ages and the masses. Some of that can come from the color magnitude diagrams using evolutionary models. But others require, you can get more precise data, for example, by looking at asteroseismology measurements of these parameters, or at least calibrate some of those models using those asteroseismology measurements. Other things like the Metalyses, measurements such as rotation, all of these need to come from some degree from either spectroscopy or time monitoring studies. So studies like LAMOST, TESS, even Kepler have been critical to kind of getting up this picture to be a full multi-dimensional space. So you can start to look at correlations between some of these parameters in new populations. And of course, probably one of the most famous of these recently is the Gaia Enceladus, or the sausage, right? This seeming remnant of an early merger of a fairly large satellite galaxy with the Milky Way, at least the proto-Milky Way. This, of course, showed up in the Gaia data, and it's important to keep in mind that this showed up because of the combination of kinematic and astrometric data plus our understanding of the Metalyses of the stars. So this top row of plots comes from the Belokorov paper, who referred to it as the sausage because in this kinematic space, it looks kind of like a sausage with an egg on it. I'm not quite sure what the diet is for that. But importantly, this really shows up in a very narrow range of Metalyses. This does not encompass stars that are the most metal poor in our population. It really starts to encompass stars that are kind of in modest metallicity. That indicates that this is not some structure in the old halo population. This is something that's coming from a distinct population, both metallicity-wise and kinematic-wise. And also when we combine, again, different metallicity measurements with the kinematic constraint, we can also start to find separated populations in here. And I remember as a grad student at Caltech that there's still being debate about whether there's a thick disk or not, if that really existed. And once you start to look at the Metalyses space, it's so obvious, right? There's no debate about this anymore. And that, of course, came from the combination of not just the kinematic and astrometric measurements showing the distribution of the disks, but also the very distinct chemical abundances within these. And there's other ways that these can be combined. So here's another example looking at Metalysis populations, again, in sort of a kinematic space with different coordinates. So on the left, you have a sort of combination of the radial and vertical coordinates and combined with the azimuthal velocity, and then mapping sort of clusters in kinematic and Metalysis space. And the Metalyses are shown on the side here. And again, you can see that there are distinct structures in here. In particular, the fact that Gaia Enceladus is kind of lying in this essentially zero angular momentum sort of line really does belie its sort of origins as an accretion event as opposed to something that's sort of formed in situ in the galaxy itself. And in particular, noting that it's a more metal poor population, but not quite as metal poor as some of these other structures, allows us to distinguish it as a separate kinematic structure and an origin structure. So it comes from a different system. So several of these different structures have popped up in here, not only just Enceladus, but also things like the Sequoia and the Thamnos, I'm never quite sure how to pronounce that. But all these different populations come in addition to the standard galactic populations that we've been talking about for many decades. But again, the important thing is that all of these studies require not just one really great astrometric survey, but the combination of multiple surveys that are bringing in multiple dimensions of information so we can start to tease apart these populations from these various parameters. Now, what's meant? So this is great. Right? This is many hundreds of theses, PhD theses. So what are we missing from all this? And I think that the issue is that many of these studies are really focused on the standard tracers of galactic archaeology, which are FGK stars and red giants. And those are great because they're bright. We can see red giants across the galaxy into other galaxies. And so we really can trace out these large scale structures in this way. But it's important to keep in mind that the bulk of the stars, at least in terms of number, are the lowest mass stars. And this can be seen not only in the Gaia color magnitude diagram, which it's important to keep in mind that this is magnitude limited by the time we get down to the low mass stars. Even the local population, as we'll see, is not complete when you get down to these low mass stars. But we do know from previous studies, for example, from SDSS, that these stars comprise at least 70% of all stars in the solar neighborhood. If we talk about M dwarfs, for example. So this lower right plot here is from a study by John Bachansky about 10 years ago, looking at the SES data set. And what you see is the stellar initial mass function. The measurements here are the red dot. This is kind of a standard log normal fit to that line. And I think the important thing to point out is that, what we typically call low mass stars or ultracool dwarfs start around half a solar mass or maybe a third of a solar mass, somewhere around here. and extend inward. So the very peak of this mass function is encompassed by these low mass stars. They really are the dominant population in our galaxy, at least in terms of number, even if they are essentially invisible population because of their low magnitudes and faint brightnesses. So in this talk, I'm going to be referring to these population of ultracool dwarfs. I just want to make sure I define this clearly. These are what we consider kind of be the lowest mass stars and brown dwarfs. There are various different definitions people use for these. For this purpose, I'm going to be talking about stars that are less than about 1/10 of the solar mass. That means luminosity is less than about 1/1,000,000th of a solar luminosity, temperatures below about 3000 Kelvin, and spectral classifications that start around M6 or M7, then go cooler from there. And so this is a plot on the right showing a kind of spectacular main sequence. This is as a function of spectral type going from B to Y dwarfs, which is one of our new spectral classes of very cool objects, and extending over 30 magnitudes in H band absolute brightness. And so I'm really talking about the kind of lowest region down here, lowest corner here, the faintest and lowest mass objects, which are going to be, as we'll see, a mixture of both stars and brown dwarfs. They're encompassing things that are actively, sort of steadily burning hydrogen in their cores, and objects that fail to burn hydrogen at any time. Now, these objects are distinguished because not only are they very low mass and cool, but they also have very complex spectra. And that's largely a factor of the fact that when you get down to temperatures below 3000 Kelvin, molecular chemistry becomes very important, not just molecular gas chemistry, but also molecular condensate chemistry. And particularly when we talk about the L dwarfs, we have to include factors of cloud formation, maybe unequal cloud distributions across these stars. We're really starting to get into kind of planetary atmosphere kind of work. And that both complicates, but also enriches our understanding of these atmospheres. When you have an atmosphere that is dominated by molecular absorption, that atmosphere is a much better probe of the chemistry, or at least the abundances of the atmosphere, than an atmosphere that where, for example, you only see hydrogen lines. So this is a really rich opportunity, but it's also sort of a complex opportunity because these atmospheres are very hard to model. There's a lot of work on this that I'm not going to talk about today, but that's certainly a part of the picture. Now, of course, I think that the real fundamental property that distinguishes ultracool dwarfs, not just their cool atmospheres, but the fact that they are straddling this regime between the lowest mass stars and things that we call brown dwarfs. And just kind of remind everyone that, when brown dwarfs are distinguished by the fact that they don't have sustained hydrogen fusion in their cores. And that means that we actually return to 19th century stellar astrophysics, where we talk about late type spectral types actually meaning older stars. So brown dwarfs start off as warm objects because of their initial gravitational heat of formation. And then over time, they cool off to become cooler and fainter objects because they are not, their loss of energy at their surfaces is not being made up by fusion in their cores. So when we talk about the sort of evolution of brown dwarfs, it's very distinct from the evolution of stars in the fact that they are continuously changing over time. And that's going to be a very important aspect of why they may be particularly useful for galactic archaeology, because they are fundamentally temporal objects. They evolve over time. Now, I've labeled on this plot that shows temperature versus age on a log scale here, different regions that correspond to things that do have stable hydrogen fusion. Keep in mind that it might take 1 billion years for that to happen. So it's a pretty long pre-main sequence phase, but at some point they do stabilize on the pre-main sequence, versus objects that are evolving through time, which we call brown dwarfs. And you can even distinguish another class of objects that people sometimes call planets that have no fusion whatsoever. I've mostly focused on hydrogen fusion, but there's, of course, other light elements that can fuse. Of course, planets, it depends on what agency you're getting funding from, what you call them. But in any case, all these objects have the same kind of similar behavior in that they change over time. They physically change their main properties, temperature over time, temperature and luminosity. And that will be very important for their temporal usage in galactic archaeology. Now, we have a very good understanding of the local ultracool dwarf population. We've been studying these objects for several decades now. This is a recent result from David Kirkpatrick, who's over there at Caltech IPAC, who's been building up the sort of local sample of the coldest brown dwarfs over time, and has now made what is currently the best measurement of the luminosity function of these objects. This is again spanning a range between about 2500 Kelvin down to the very coldest classes, which you can see gets down to about 300, 400 Kelvin. So, the room temperature, that's still mind-blowing even to this day. And you can see that, for example, the luminosity function is actually quite interesting. It peaks as we go to cooler temperatures. And so even though the mass function peaks at masses between, around 0.1, 0.2 solar masses, the actual population of ultracool dwarfs is probably actually all piled up at the very coldest temperatures. And that has everything to do with the fact that they've just had plenty of time to cool off over time. Anything that's substellar is going to have, the age of the galaxy to cool off from whatever its form. And so we get this pileup of very cool objects.
And Adam, we should take this as being a complete sample, roughly?
Almost, yes, almost. So it's certainly not volume complete. So there are corrections that have to be made as you get to the low temperature range.
And that hasn't been made yet in this, what we're seeing.
This has been volume corrected, yeah.
Okay.
So the actual sample is not volume complete, but this has been corrected for any volume completeness that exists in the sample. Up to when you get to these low temperatures, the distances where we can detect 300 Kelvin brown dwarfs is a few parsecs. And so this is almost certainly a very low limit for what the actual population is here.
And the little peak near 1300, is that real?
Yeah, that's real. And so that is, we think, an effect that comes from, I mentioned the clouds forming in L dwarfs. At some point, that those clouds are a source of opacity. So they actually slow down the evolution of brown dwarfs in that phase. And so you get kind of this pileup of objects at this particular temperature. And then below this, the clouds somehow, we still haven't quite figured this out, somehow disappear below the photosphere, and the objects become essentially transparent again. So you get kind of a rapider phase of evolution. So that pileup is an atmospheric effect, which is kind of interesting, and that's part of the evolution.
Yeah, cool.
Adam, yeah, so this might be a little bit off topic, but with several thousands of this kind of warm, really nice temperature, 300 Kelvin, substellar objects, right, per cubic parsec, wouldn't this be like the most likely place in the universe to find life, or for life to happen in this? Can life happen in this atmospheres of these things?
So there's a little body of research on this, and and I should also say there are folks who are specifically looking at brown dwarfs for planet detection. There's been no exoplanets found around a brown dwarf yet. TRAPPIST-1 is actually a low mass star, so it's not it's not in that regime. There's a couple of problems with brown dwarfs. One of the main one is that they change with time. So you might have a planet that's habitable for a little while, but then it's going to freeze. And when you get down to 300 Kelvin stars, you got to actually stand on the star to have a nice day.
Yeah, that's what I'm talking about. I'm talking about like life on the star. Not
okay.
Can the chemistry happen? And is the energy there? Can there be like liquid water in the atmospheres of the stars?
So the answer is yes. I mean, the models for Y dwarfs have to account for water condensation, which is, if you know anything about the spectra of cool stars, water gas opacity is very high. And so if that gas goes away to liquid, it completely changes the opacity structure of the atmosphere. So that's actually a really tough model. Carolyn Morley has done a lot of work on this at UT Austin. The astrobiological implications, I think, are still speculative at this point. I mean, it's kind of asking, could you have life in sort of the clouds of Jupiter deep in? There's a question whether you can actually, form stable molecules that will, start to evolve over time in those conditions. The other problem, of course, is that they're 300 Kelvin now. They weren't 300 Kelvin a billion years ago, and they won't be 300 Kelvin a billion years. So, maybe they settle with time. But I think that's an interesting speculative astrobiological question.
Thanks.
Yeah. Okay, so we have these objects. We know they're out there. We know they're very abundant in the solar neighborhood. And of course, one of the problems with using them for galactic archaeology studies is that they're just so darn faint, right? So they really dip down in brightness as you get to lower temperatures, as you would expect. These are the 1 kiloparsec detection limits that you would need to have in order to detect these objects as a function of spectral type in various surveys. And you can see that, even with Gaia, even with, to some degree, Vista, you're not really detecting any of these objects at the sort of 1 kiloparsec level, which you would really like to get to if you want to study larger structures in the galaxy, to go beyond the solar neighborhood. So this is really a sensitivity limited game, right? Until we can achieve these kind of levels of sensitivity, ultracool dwarfs just aren't built up at the numbers or the depths that they would be useful for galactic archaeology. And so we see this when we look at Gaia, for example. We know that Gaia is not complete to ultracool dwarfs, even in this local solar neighborhood. This is a somewhat complicated plot made by Chris Tyson, but the key point here is that even when you account for just the stellar ultracool dwarfs within 20 parsecs, the Gaia survey is actually largely incomplete to them. And the incompleteness gets worse as we get to lower temperatures and later spectral types. And at some point we completely lose most of the brown dwarfs to Gaia because it's an optical survey, so it's not going to detect these essentially optically invisible sources. But you see, these objects are also missing in some of the catalogs that we use to kind of feed in to produce these multidimensional data sets. And so I like to show this to kind of shame all the all the folks that work on these things, right? If you look at all their plots, they all end at 3000 Kelvin. So here's the Kepler input catalog, and they've got nothing in here that's below 3000 Kelvin. Kepler has observed many ultracool dwarfs below 3000 Kelvin. They're just not at the numbers that you would have to show up on this plot. Here's the test input catalog, 3000 Kelvin, right at the limit. Here's the Apogee ASP so the modeling code that actually takes the high resolution infrared spectra from Apogee and turns it into parameters. That code stops working at about 3500 Kelvin. So if you go into Apogee and you look up some of these objects, they have no physical parameters attached to them because the models aren't designed to work in those temperature regimes. LaMost, it stops at 3000 Kelvin. Lots of these surveys are missing ultracool dwarfs, and they all seem to end their plots at 3000 Kelvin, which is where we start our science. And it's not just the observational data where we're limited, it's also even in the modeling itself. And so a lot of folks that are modeling the populations in these surveys, combining Metalyses and main sequence color magnitude diagrams, use the MIST models or the Parsec models, and the MIST and Parsec models are also limited at about 3000 Kelvin. So these are plots from the MIST isochrones. Here are the Parsec isochrones. You can see that the lowest mass they show is a tenth of a solar mass, and that's where I start my science. So one of the big challenges of doing this work has been to have not only the data, but also the models to actually do the work to represent these sources. And again, the reason is that they're so faint that they form a minority of the population in these surveys. And so, and the physics of their atmospheres get so complicated that it's a big step to take if you're trying to do galactic archaeology, because they're not really that numerous to play much of a role. So why then we would care about ultracool dwarfs? If they're so rare in these surveys, if they're not going out to large distances, what's the point, right? Why don't I just treat them as sort of the little house pets that they are, just local neighborhood things? And hopefully I'm going to convince you that there are some really unique properties of ultracool dwarfs that if we can implement surveys that define these in large scales, and as I'll see, we will have those shortly, they'll actually be able to answer some very unique questions. So again, it's important to keep in mind that ultracool dwarfs are extremely common in the galaxy. They're found in all galactic environments. So obviously, very early on, they were found in young clusters. We have found brown dwarfs that are halo orbits, the metal poor objects that are in halo orbits. We have candidates and globular clusters. We'll hopefully resolve that question with James Webb in the near future. They are the most common, they're far more common than the FGK, dwarf, and red giants populations that we use to study the galaxy, at least on a sort of local by volume scale. But more importantly, they're extremely long-lived, right? So, M dwarfs themselves live to be about 100 billion to a trillion years. So you don't really have to worry about the age of the universe at that point. They're just going to be there. That means every single one of these stars that's ever formed is still around. And of course, when you get to the brown dwarf regime, there's no meaningful word for lifetime because they don't die, they don't fuse hydrogen. So they are just around, they never go away. So you don't have to worry about the sort of limited lifetime effects or the evolutionary effects of these objects as a tracer population. Because of that evolution, as I mentioned before, these objects can become relatively good clocks, at least from in principle, because their bulk properties are changing with time. So I'm showing here is kind of two evolutionary studies of a sort of warm ultracool dwarf, so something that's about 2500 Kelvin, and a cold ultracool dwarf, something that's about 1000 Kelvin. And what I'm plotting is if I assume these properties at today, so 10 billion years since the formation of the galaxy, for example, what I'm looking at then is how different bulk physical properties, so this is not rotation, this is not lithium abundance, this is the bulk properties, radius, luminosity, and surface gravity vary over time at that given temperature. And you can see that they vary quite a bit. So for example, this line here is showing the surface gravity. And the surface gravity varies by almost a factor of 30 between ages of about 10 billion years up to 1 billion years. Now, these are because very young M dwarfs are substellar, so they're changing over time. At some point, you catch up with the mass at which these objects are fusing. And after that, these objects don't change at all. In fact, something that's a stellar M dwarf that forms early on in the age of the universe has barely fused any of its hydrogen at that point. It's such a slow fusion process that it's a fairly chemical homogeneous source that's around for as long as you want it to be. And so at young ages, these warm brown dwarfs become very good in terms of temporal variations. For cool ages, these objects evolve throughout the age of their lifetime, right? So you have a continuously evolving object that you can use, again, if you can break up some of the degeneracies to place this object on a particular age and mass, and therefore get some information about both those properties. Now, a really interesting thing is when we combine stellar and substellar populations, because these objects may form at very similar masses. And of course, early on have roughly the same temperature because it's just again, the heat of formation from gravitational collapse. But if you wait 10 billion years, for example, a globular cluster, these populations will have diverged considerably. And so one of the things that we look at, for example, is as we get to these older populations, globular clusters, or in the halo, we should start to see gaps in the main sequences that give rise to this evolution. And that gap, the width of that gap, becomes another temporal measurement that we can use for studying populations. We already use brown dwarfs for age dating systems. I should keep that in mind that very early on, it was recognized that lithium, which is a light element that's destroyed at slightly lower masses than the hydrogen burning limit, can be depleted on timescales of tens to hundreds of thousands of years for objects above the lithium burning mass, which is about 0.06 solar masses, but is preserved for masses below that. And in fact, this was one of the first tests to identify the first brown dwarfs, is to see if it had lithium in its atmosphere. So you can see the lithium line here in a piece of spectrum down at the bottom. So not only is this a brown dwarf indicator, but because this, the depletion of lithium takes us kind of a range of time, because it just takes time for the lithium to mix through the core and deplete from the atmosphere. This has been used as a clock for young clusters for quite some time. So here's just one recent example looking at Blanco 1, showing the lithium abundance measured in stars. You can see that in the sort of higher mass stars, these objects retain their lithium because they're just separated by the radiative boundary layer. So the lithium isn't actually making it down to the core. But as they go to lower masses, these objects are fully convective. The lithium is depleted down in the core. But as we get over here, we start to recover that lithium because these are objects that aren't actually fusing lithium in their core. So again, the gap in where this sort of lithium boundary reemerges is a measure of the age of the cluster, and that's been used successfully in many systems like this. So we already have examples of using these for time, so we can imagine using them for other populations as well. I also mentioned that because of the complex molecular chemistry, these objects are very sensitive to variations in temperature and gravity, as well as abundances, as well as other things like clouds and mixing. So there's actually quite a few parameters. But that sensitivity means that we have a stronger handle on some of these core physical properties than we might necessarily have for normal main sequence stars. This is just showing a series of different spectra that all have the same spectral type, but they have different infrared morphologies. And those infrared morphologies come largely from issues of surface gravity, from metallicity, and some other mixing effects. So we have a huge diversity of spectra, and that diversity maps into a set of physical parameters that we can measure. Now, why? So that's, so those are some of the benefits, but here's some other things that we can actually ask with ultracool dwarfs that we can't necessarily ask with other stellar tracers. So one of the questions that we could ask, for example, is the history of early star formation. Was it top heavy or bottom heavy? The standard paradigm is that when you're in the sort of early stages of star formation, early in the universe, metal poor environment, usually more massive systems, that the mass function favors the production of high mass stars, right? This is a couple of studies produced by Marxell 2012 looking at the mass function based on the population of globular clusters. And the canonical value is about 2.3 for the mass function index. That's our salpeter value. But as you go to both higher cloud densities and lower metallicities, it appears that mass function becomes shallower, which means you're getting more high mass stars than low mass stars, relatively speaking, to the sort of standard IMF. Now that's studies of our globular cluster systems. That's not necessarily representative of the galaxy at large. And there are other studies that have been looking at nearby elliptical galaxies and doing composite spectroscopy, and particularly focusing on lines that are formed by the M dwarf populations in these systems. So these are things like calcium-2 and magnesium lines. And what they've inferred from those analyses is that, in fact, those systems seem to be more productive in low mass stars than high mass stars. And in fact, they're kind of super salpeters. So this is an example showing the spectrum of this particular system, NGC 1407. Again, this is the sort of central region of this elliptical galaxy. And then sort of the principal components of the spectra that make up this composite system based on high mass to low mass stars. And using the sort of pieces, the sort of additive pieces that make up the spectra for these systems, they can infer a overall number density for those populations. And that number density seems to rise much more steeply than it does for the normal salpeter function. And in particular, notice the mass range here extends into the ultracool dwarf regime. So the most abundant stars in the system are the lowest mass by far more factor than it is in our local solar neighborhood. So there are some questions as to whether early star formation processes are top heavy or bottom heavy. Of course, that has an implication on the star formation process itself.
Is there an easy explanation why this would happen?
I don't. I don't.
Okay.
I'm not sure. And it's been repeated. So there's some controversy about this because people do worry about the use of these indices and what other stellar components can go into them.
Mm-hmm.
I know that the Conway team has been building up like larger samples of giant stars to see if that's a contaminant population. But so far, all these results have been repeated that in some of these systems, and not all, but some of these systems, they seem to have a super salpeter mass function.
Okay, thank you.
Another question that brown dwarfs may be particularly useful for are studying the primordial lithium abundance. I think many of you know that there is this persistent tension between the abundances of lithium in the oldest stars for which we can measure them. That's the abundances here measured by the Spite plateau. And the essentially predictions that are needed for Big Bang nucleosynthesis that are sort of verified by the cosmic microwave background measurements. And so that's, a factor of 5 to 7 or something like that difference in those measurements. And that just hasn't gone away. It's been around for quite some time. And so one of the problems, of course, of using these stellar tracers is they're stars. And so they are fusing lithium in their core. And there will be some evolution of the lithium abundance throughout the star, even in the case where you have sort of a radiative boundary that prevents the lithium from going through at high rates. So one very, I would say, not, stellar astrophysics, so not particularly like, cosmologically exciting reason where you have this lithium difference is that it's just lithium evolution in stellar interiors. If we have a population of objects that don't do anything with their lithium because they're not hot enough to fuse it in their cores, that is a potential tracer population where we can make studies of this particular property and see if we can actually see if there is a difference between the early population of brown dwarfs that formed their lithium abundances and the predicted abundances from Big Bang nucleosynthesis. That, of course, requires finding those very old brown dwarfs, and that's still an ongoing study. A third case that we've been talking about recently is this question about how the thin disk is heated. And this is still also an open question. We know that when we look at different stellar populations that have different main sequence lifetimes, and this is a very old result, right? We know that they have larger dispersions of velocities, they extend over larger scale heights, and that's generally sort of attributed to various disk heating processes. It could be dynamical scattering from molecular clouds. It could be sort of these perturbations that we see from the spiral and bar arms. And it could just be the sort of stochastic perturbations that come from satellite interactions with the Milky Way. Each of these ideas have actually a different mass dependence on the perturbed population. So you can imagine scattering would scatter more low mass objects at a higher degree than high mass objects. And so it's potential that we could look at the mass dependence on the scattering to see if we can disentangle these different effects. Now, we can't do that with these high mass stars because we are dominated by their main sequence lifetimes. But remember, past about half a solar mass, none of these objects are going to evolve off the main sequence. So they're here for the entire time. And so, for example, you can imagine that if there was a mass dependence on, so I just took it, for example, as kind of a toy model, a typical velocity age dispersion relation. If you apply a mass dependence on these things, you can actually get different patterns in the dispersion relations. And so in principle, you could test whether some of these mechanisms are more dominant based on their mass dependence in the dispersions of the populations as you go to lower masses. All right, so I'm running out. I'm going to make sure I get close to time. So I'm going to do really quickly kind of the results of 2 Pathfinder studies, and I'll probably really quickly breeze through sort of what we can expect in the near future. These are 2 studies that have been done by a couple of my grad students here at UCSD. And again, with the goal of kind of looking at, can we use what we currently have for UCD populations to start to at least test what are the likely outcomes of doing these programs with deeper and larger UCD populations where we have this complex multidimensional data set. So this first one is my grad student, Dino Siu, has been looking at radial velocity measurements or making radial velocity measurements using data from the Keck NIRSpec instrument. There's over 20 years of archival data with this instrument for ultracool dwarfs, many of which haven't actually been reduced yet. So he's actually been doing, as part of his thesis, going through and forward modeling these spectra to produce very accurate measurements of their radial velocities in V-side eyes. And for the exoplanet folks, for us, accurate is half a kilometer per second. That's great for us. So this is not your level of accuracy, but it's good enough for galactic archaeology work. So here's kind of the scatter diagram of his samples. You can see that these are small samples. So he's only got about 30 T dwarfs in the entire sample, and then something on the order of 90 or so late M and L dwarfs. This is not a typical galactic archaeology population, but this is at least a start to see what do we see in terms of population parameters. Now, again, with this idea that the populations disperse over time, when we look at sort of the scatter of these objects in kinematic space, we would expect that would track with the population ages. And it actually turns out that this is a little bit more complicated for ultracool dwarfs because they are evolving over time. So some subsets of spectral types may be younger, not because those particular stars have to be younger. It's because they're passing through that phase of evolution relatively quickly early on in their career. So that's kind of where they are for that particular temperature. So it's a little bit mix of mass and age. So this is kind of a schematic of his, so he's taken these measurements and now he's modeled these using kind of a simple forward modeling population. He generates sort of distributions of masses and ages and binaries included in there as well. He evolved those in time to get their present day physical parameters, and then he maps those physical parameters to empirical relations that give the spectral type of those objects. And then parallel, he's applying age velocity relations, kind of standard age velocity relations we use for nearby stars. And he has now a combination of spectral type and 3D kinematics that he can compare for different assumptions about population parameters. So that's kind of the goal, is to vary this sort of first box here. So this is one of his results, and so I'll walk through this just really quickly. So what you're seeing is a little bit complicated, but this is kind of showing the multiple distributions that he's made. The gray band here is the initial sort of input age distribution for that particular population. They're not the same because, again, brown dwarfs are evolving over time. So for example, even if we choose a uniform age initial star formation rate, the T dwarfs will tend to be older because they've just evolved to that point. The yellow band is what you would infer for the distribution of ages based on kinematics alone. So taking the initial population, simulating the kinematics, and then applying a kinematic experiment to get their ages out. And then the blue points are what he's actually measured in this RV data set. Now you can see here that the measurements and the predicted distributions are pretty good. This point here is when we took the original sample, we actually found that the L dwarfs were much older than they were expected to be. And this is a result that's been going back now for about 6 or 7 years. And no one could quite understand why the L dwarfs were older, because all the models predict them to be younger, because this is a sort of temporary phase of brown dwarf evolution. And what he's realized is that, in fact, this population is contaminated by thick disk members of the galaxy. The nearby solar neighborhood, of course, contains all the populations, but at extremely small fractions. And this is a small sample, and we didn't expect there to be a lot of thick disk objects, but it turns out that our local population has a lot more thick disk stars in the L dwarf regime than contaminants in the other 2 populations. So that is also telling us something about the local population to some degree. And then you can turn that and then apply the sort of same models for different assumptions about things like the star formation rate and the age of the population, and make constraints based on that. These are just numbers of chi-squared, showing that there's some degeneracy, but there's at least some places that it can rule things out. Now, one of the interesting things that came out of this study, looking at in more detail, is he actually is able to show that kinematics can probe the hydrogen burning minimum mass. So remember that these objects are a mix of stars and brown dwarfs, but as you get down to a minimum temperature, the stars drop out because you just can't have stars that are that cold. And what we see at about that temperature, which is indicated by this dashed line, is a sudden kind of hiccup in the kinematics. These objects kind of go up in age or go up in dispersion until they kind of drop back down to the sort of trend that goes across the entire L-dwarf sequence. So we think what we're seeing here is kind of the last gasp of stars that are mostly old, right? They're things that can be around for as long as they want. Very few brown dwarfs in here, and then we switch over to entirely brown dwarfs. So not only are we probing galactic structure things, but we can actually use these kinematics to look at the evolutionary properties of brown dwarfs. And for example, pin down, does that mass that corresponds to that particular spectral type line up with what we expect for the hydrogen burning minimum mass? All right, so we've learned several things. For sake of time, I'm going to walk past there and just kind of point out that we've at least demonstrated that we can do this work, but the samples are still too small to really do a great job with it. The other study was done by another grad student, Christian Aganze, who's been using the WISPs and 3D HST WIFC3 parallel survey. So all of I've talked about ultracool dwarfs is based kind of within the inner 50 parsecs around the sun. Again, if we want to really understand galactic structure, we need to go to kiloparsec scales. And these surveys actually provide that opportunity. So this is just showing sort of the pointings of the WISP fields. This is an example of one of the L-dwarfs he found out of about 200,000 spectra that were obtained. Most of these are high redshift quasars and galaxies. That's what most of the folks care about. We just get the little kind of residual foreground stuff. But it turns out this is the largest sample of deep ultracool dwarfs that has been found so far. It's about 160 sources. Again, not a galactic archaeology sample, but a first step in sort of doing this for ultracool dwarf science. Let's skip through here. So applying kind of a similar structure, but using a galactic structure model to predict the distances of these objects, Christian has been able to model the star counts as a function of spectral type in these different bins and compare to the models for different scale heights. So that's the main thing that we're measuring here is how do we sort of model these star counts based on scale heights? And in fact, he gets a fairly consistent measure of the number counts we'd expect. Keep it in mind that our numbers are very low when we get down to these coolest objects, right? These are in sort of single digits down here. And then you can take the scale heights and turn those into population ages as well, and then do the same comparison that we did with the kinematics. So you can see, for example, that he's able to show that, in fact, there is a decrease in the average age of L-dwarfs in this population. Past that, it gets pretty hairy because we just have very few objects, but we at least see some structure that's starting to emerge from these kind of measurements, at least for this small population. Okay, so let me transition and just real quickly kind of summarize that, all of these are based on what data we have available today. In the near future, we're going to have a much deeper sample, and I want to make sure to argue that, these samples are going to have plenty of ultracool dwarfs for us to do these work, not at the level of tens to hundreds of objects, but hundreds of millions to billions of objects in some cases. One of these is the Euclid Survey. This is going to be doing a deep survey down to magnitudes of 20 to 21 in J and K. Remember that that's the point where we start to see particularly the L-dwarfs at 1 kiloparsec. And so we expect in these wide surveys to be getting to, just skip here, no, that's not it. If you look on the right side here, this is kind of the number of objects we expect as a function of spectral type. And you can see that we're getting millions of sources per subtype bin, all the way out into the T-dwarfs, at least for the disk population. And we're getting thousands of objects also in the halo populations as well. So it's going to be a really big sample that's allow us to do these measurements in much greater detail than we can today. Another one is the Nancy Grace Roman wide field imager that's going to be observing in these kind of asteroid space invader pictures over the course of the sky. Keep in mind that this 0.3 square degree of sky is the entirety of Christian's WISP sample, and that's just one exposure. So this is greatly going to increase the number of objects in that kind of sample. And again, it's going to be able to reach things in different kinds of surveys at the numbers of sort of, distances of several kiloparsecs in scale, and numbers that are again in the kind of the millions per subtype bin, depending on the survey. And importantly, both Euclid and Nancy Grace Roman are going to have Prism surveys as well. And that means that we're going to be able to get Prism spectroscopy, so classifying spectra across these regions. And again, in numbers that add up to kind of thousands to tens of thousands of objects down to the T-dwarfs. So that's going to be a really greatly detailed survey as well. James Webb, of course, is going to be very effective for parallels and gets down to distances that are going to be many tens of kiloparsecs. So in fact, this is showing sort of the cumulative number density of sources for ultracool dwarfs as a function of J magnitude. We're getting down to the 30s here. You can see these numbers kind of flatten out because we actually get to the end of the disk in these studies. And so we're actually able to measure the entire disk and whatever its scale height is. And we will have a parallel survey that's approved for the first cycle. This is a JWST passage survey. And that, again, looking at simulations, we'll be able to find hundreds of fields. We're going to be finding hundreds of brown dwarfs total, thousands of brown dwarfs total, which we have spectrum. We can start to make measurements of not just the number counts, but also as a function of metallicity, because we'll have the full spectrum to make those measurements. And finally, I'll just point out that these surveys are going to be really starting to hit ultracool dwarfs at populations that we really don't think of as ultracool dwarf science. And so things like James Webb are going to be getting out to the LMC, Sagittarius, 4L dwarfs. And so we have the possibility of even looking at these populations in these other satellite galaxies for the first time. And of course, we'll be getting to T dwarfs that if we're at kiloparsec scales, that means that we're starting to probe the bulge and the Milky Way center for these populations, where we do have evidence that star formation produces slightly different mass functions. Okay, so I'll stop there and thank you for your patience. Sorry I took the whole hour there, but I'm happy to stay on and take some questions, and hope you're as excited as I was, I guess, 10 or 15 years ago about ultracool dwarfs, but in this case in the galactic context. Thanks very much. I'll take your questions.
Thank you. That's a really nice summary of all that science. Does anybody maybe raise your hand, or you can just come on if you could take a couple questions? Okay, go ahead.
Thanks for the talk. Very nice talk. I was just wondering about what you were saying about the speed plateau and the lithium abundance in the stars. So my question is, lithium production in the galaxy starts at about at a metallicity of about -0.5. So are these brown dwarfs? Does these brown dwarfs have lower or higher metallicity than that? Because if they're lower, maybe you are directly measuring just the Big Bang nucleosynthesis lithium.
So we do see brown dwarfs that have overall metallicities that are below -2. There's not many of them because, again, these are halo objects that happen to be passing through the solar neighborhood. So there's like a handful of these things. So in that sense, we are finding fairly extremely metal poor. So I also work with IAC collaborators that really study metal poor stars that are like FDH -5 and -6. So we're not there yet. That's mostly numbers, but certainly we have evidence that these objects are forming in the larger halo. They have retrograde orbits, so they're probably things that could potentially have been formed early enough on that they're probing at least close to the primordial lithium abundance. We'd have to get really much earlier, right? So this really does require big enough samples where we're finding the hypermetal poor equivalents. And I should say the other complication of this is that remember that these things evolve. So they're not L dwarfs, they're T dwarfs, maybe even Y dwarfs. And at those temperatures, lithium is actually condensed into lithium chloride. So we can't actually look at the lithium line anymore. And this is a result that Nicholas Ledoux published a few years ago. We're gonna have to look at lithium chloride molecular absorption in the infrared. Okay. And that is something that's possible with James Webb. And there was a recent study led by Mark Marley's team on looking at that.
Okay, but I honestly do not think you need to go to hyper metal poor stars, -5, -6. I think -2, -2.5, you are already probing the primordial lithium, if you can.
That would be great, because we at least have a couple of those objects.
Yeah, I do not think you need to go to -5. I think -2.5 is safe, because lithium in the galaxy it's -0.5. Well, maybe a little bit lower than that, but definitely not -2.
Okay, thanks for that.
Thanks.
One additional question I had was, you showed through your talk, you're really sort of at this cusp of having just an amazing sample of these cool stars. And what we like at the same time is theoretical models to interpret these observations that are sort of at the right fidelity level. So how, where are the theoretical models? I can imagine, especially for cooling and aging things, there's a lot of physics in terms of magnetic fields and star spots and clouds. And so is the theory up to, at the level for this sample that's coming soon?
Well, so we'll see. I mean, I think part of the reason, so one of the areas that I think needs to really develop is as we start to probe these particularly old populations, the key thing is looking at brown dwarf models that take into account subsolar abundances or non-solar abundances, really. And one of the reasons that hasn't been delved into deeply, there have been a couple studies looking at metal poor brown dwarfs for sure. But the number of those objects that exist in which you can test those models on is relatively tiny. I mentioned that we have one candidate globular cluster brown dwarf. No one's quite sure that that's really there, but we have a photometric measurement, right? So it's hard to make real models for that. And because there's so many ingredients to these models, you do have to take into account fairly complex chemistry, non-equilibrium chemistry. There's vertical mixing that's happening in the atmosphere. Condensate formation is a very complicated process, not just on brown dwarfs, but on the planet Earth. So, there's a lot of detailed physics that has to go into this. And because of the sort of the challenge of making those models, even for solar metallicity, much of the work is focused on that and seeing if we can get the solar metallicity brown dwarfs correct. And, things like retrieval modeling has helped advance that a little bit, but it's still a lot of computational effort to do these kind of complex models. So one of my third grad student, Roman Gerasimov, is actually working on non-solar abundances because we know with James Webb, and we actually have a couple of proof programs for globular cluster studies of brown dwarfs, that we will be picking up some of these objects in those color magnitude diagrams. So the motivation that we will have the data has started to push the production of some of these models. But I suspect that once we start to make these models, we're going to find that we're missing some pretty key ingredients, even at these metal poor. I should say the metal poor models are a little easier because cloud formation is, of course, it's condensate formation. So it's the stuff like iron, liquid iron and vanadium oxide. When you reduce the metal content of the atmosphere, those clouds kind of disappear because you just don't have enough material to make them. So it really comes down to how do we deal with the opacities of these different molecules with these non-solar abundances. So I think it's doable. It's just, it takes person efforts to do it.
Yeah, it sounds like there'll be the motivation too, especially in the near future. So, Andy can give us our last question. Go for it.
Okay, so maybe I missed this bit, but you talked about thick disk L dwarfs, and maybe I missed what the conclusion was. But what does this do to the thick disk IMF? I mean, just do the numbers you have fit in with what you'd see from the brighter, hotter thick disk stars in the thin disk or locally?
Yeah, great question. So for Dino's study, what we realized, if you look at kind of like there's this kind of typical measure of the sort of probability from a kinematic perspective whether an object is a disk or a thick disk. So this is based on Bensby et al. 2003. And what we found is that statistic, we had more objects at sort of the thick disk end for the L dwarfs than the late eminent T dwarfs, but that was like 4 or 5 objects. So that wasn't enough to really make any constraints on the thick disk IMF. And conversely, when we model the thick disk IMF in there, and just using kind of standard, Jurek et al., for example, parameters from Sloan, you do get something like on order of 1 to 2 thick disk objects that you would expect throughout the whole sample. So it's a little higher than we expect, but not at the level that we are, that we're concerned. Certainly, if we can expand the sample, so that's a sample that only goes to 20 parsecs. If we expand that sample out to 30 or 40 parsecs, I suspect that we'll have a much better handle of what those stars are, and if that's an unusually high fraction, but we just don't have the numbers yet.
Okay, so I didn't understand when you were talking that it was that small number statistic. So that makes total sense, but it would be, like you say, really interesting once you have a bigger sample.
Yeah.
Yeah, thank you.
Yeah.
All right, well, thank you again, Adam. It looks like your schedule is pretty full in the afternoon, but if other people have other follow-up questions or discussions, feel free to reach out to Adam. But thank you, Adam, for a great talk, and everyone have a nice day.
All right. Thanks for coming, everyone.
Thanks very much.